This is Lab 4 Oscillation. Introduction. The purpose is to analyze the oscillation of a spring mass system experimentally and compare it to a computational model that focuses on the energy principle. The two models that we'll have is the computer model, which will be created through GlowScript to simulate a spring mass system oscillating with initial conditions extracted from experimental data, which is the second model that is analyzed in Tracker. Note that the system is the mass in the spring, and then the surrounding is Earth. So some important principles and equations are shown below that are crucial to this lab. The energy principle states that the total change in energy of a system is proportional to work done on the system plus any transfer of thermal energy, which this lab focuses on gravity potential energy, spring potential energy, and kinetic energy. That all adds to give the work, which is zero. And Newton's second law is also used to give the velocity and position update formula that's needed for the code. Okay, so here's the result preview. The difference or change in total energies can be zero, and the experimental data and computational model is relatively similar. So moving on to the models. Okay, so here is the experimental video that's analyzed in Tracker. The last part sped up. Alright, so the experimental data. So after setting all the points in Tracker of the spring mass system in motion oscillating, a graph with x position versus time and y position versus time is displayed, both showing an oscillating sine wave pattern as seen in the slide. Before getting started on the computer code, there are some variables we need to solve for using Tracker data like t and k. So t is the oscillation period defined as 2 pi times square root of mass over k. Without having k first, you can use the first 3 oscillation periods from Tracker, take the average of it by dividing by 3, which gave me 1.593 seconds. And so what is k? K is the spring constant, which can be solved for with the earlier equation by subbing in t that was found and solving for k, which will be 6.25 in this case. And with this information, the L naught can be found too, which was 0.07. Here's my computer model code. So I'll start off by inputting initial conditions by setting the oscillation period and k spring constant to be what I calculated earlier, the mass to be 0.402 given in instructions, time to be 0, delta t to be 1 over 210, initial position from Tracker, and lastly initial velocity to be the 0 vector indicating motion starting from rest. So starting at line 86, we set up the key physics. First, we define the vector L, which points from the spring's attachment point to the ball, telling us both the length and direction of the spring at any moment. From L, we calculate L hat, and we then initialize our 3 energy quantities, kinetic energy using 1/2 mv squared, gravitational potential energy as mg delta y, and spring potential energy as 1/2 ks squared, which will track throughout the simulation. Inside the calculation loop, 2 forces act on the ball. Gravity pulls straight down, and the spring force, which automatically points back toward the attachment point when stretched and away when compressed. These combine into a net force, which we use to update the ball's velocity and position each time step using the momentum principle via the position and velocity update formulas. Okay, here is the code output showing the computational model of the spring mass system in motion after inputting the text file with the data gathered from the experimental video analyzed in Tracker. The video is sped up here. Discussions. So comparing the data from the two. Overall, the computational model did a good job predicting the motion of the spring mass system. The x position matched the experimental data very closely throughout the entire run. The y position showed decent agreement but drifted out of phase over time, likely due to small errors in our measured spring constant and relaxed length, as well as the fact that our model doesn't account for energy lost from air resistance. Despite these small discrepancies, the model successfully captured the general behavior of the system, validating the use of the momentum principle and energy principle to predict this type of oscillating motion. So what does it mean? For your model system, is the energy principle satisfied? Just fire your answer by discussing briefly your plots of energy changes. So because there's no work done by the surrounding on the system from the model, the energy principle is satisfied. This means that there wasn't gain or loss of energy from system into the surroundings. The second part, using the data you obtained in Tracker, make 2 separate estimates of oscillation periods, first by estimating the period of oscillation from the x position data, and second by estimating the period of oscillation from the y position data, and then compare the 2 estimates. So the oscillation period for the x position data was calculated to be about 1.567, and the oscillation period for the y-axis is about 1.376, which means depending on which axis data you choose, you will get different oscillation periods. Conclusion, here are some of the sources of error. One being the human error, so extracting data from tracker, like setting the point mass in each frame or setting the calibration stick, might be a little bit off. And two, the model assumptions. Model is not representative of real-world scenarios, as certain assumptions are made, like no energy loss in the system, which is untrue in real world, in order to simulate in ideal conditions, which is not the case in, again, real-life experiments. Thank you.